All right. Hello, everybody, and welcome to the Download Community Tech Talk, Episode 11. My name is Bob Foreman. I have the honor of being the moderator for this presentation, substituting for Jessica, and I'm happy to get this thing rolling. So, welcome you. We're going to go to our first slide. And a couple of points here that we talk about every tech talk. First of all, share your experience if you're on Twitter. There's our handle for hashtag HPCC Tech Talks. Also, if you have a question regarding any of the presentations, please, you'll see that there is a interface below the presentation where you can type questions, and we'll prioritize them and get to them in the order that they happen, and sometimes the importance of them. Also, we'll have polls throughout each presentation, so you'll be prompted to answer some simple questions. And most important, we want to welcome your feedback. So rate us today before you leave. Visit our blog for information about the event. And if you want to be one of our featured speakers coming up this year in 2018, please let us know. The email is techtalks@hpccsystems.com. So without further ado, let's get rolling. It is my honor to introduce to you the epitome of energy, the epitome of excellence, and has a work ethic that I aspire to. He's our Vice President of Technology, a RELX Distinguished Technologist with LexusNexis Risk Solutions. You all may know him already, Dr. Flavio Villanustre. Good morning, Flavio.
Good morning, Bob, and you always give me a big laugh before starting. Anyway, hello everyone, and thank you so much for being here. I expect that today will be, again, one of these great calls covering a number of core topics for the community. As you can see on the slide on the screen, right now we have a few basic items to cover on our new versions. We have 6.4.10 out. We have a 6.4.12, which is an RC1, but the gold version is around the corner, pretty much. And as important or more, we have our 7.0 version, which is planned for April, May. It's going to be early Q2 release, and it has a number of enhancements and new capabilities. The change to a new major version number is not a coincidence. This includes truly quite a few core changes and new capabilities into the platform. Some of those are listed there, and it will be very long to explain some of them, but I think the ones that are self-explanatory certainly is the Spark integration there. There are also capabilities around dynamic record format, record structure translation. So your running ECL code at runtime can resolve field names from data based on the data that you have in your existing data sets or work units, which is also quite useful for a number of capabilities. And certainly a number of other integrations additionally to Spark, including the VS Code integration as well. So I really think that this will be yet another successful 7 line of code where lots of features will be added right now, and it will eventually stabilize over the first few months, but it should get you capabilities that you were asking for a very long time. Now, we do have a couple of other items to cover which are more immediate. It is certainly the fact that we have a couple of blog entries which are also neat, very neat. The one on machine learning demystified, this is written by Roger Dev, one of our core machine learning developers. It gives you a good, nice and smooth ride introducing you into machine learning and of course HPCC support to machine learning. The other one is an introduction to our Tableau web data connector. This is quite useful because in the past you needed to potentially move your data out of HPCC to put it in a relational database to use the ODBC connector for Tableau. Now we have a way to do this transparently, and I think this is also going to be quite disruptive because there are lots of people using Tableau out there for data analytics and data visualization. And one last thing from this, before I introduce the people on this presentation, is the fact that our proposal period for our summer internship in 2018 is now open. Please, if you have people that would be interested or benefit from an internship, please tell them to do not sleep until the last minute to come up with a proposal. We have a public roster of our ideas in the ideas list. There is a link there on this slide. There is also a wiki that has tons of information about how to write a proposal, has examples of the past proposals, has ideas on how to structure it and others. So it's a good resource. But of course, if you have questions about how to submit it, just contact us. You know us, you have our contact information, and you have my email address there. Please contact us if you are hesitant or have some questions or new ideas, and we'll work out something. So do not wait. That's quite important. And before going through more on this, I'll just introduce our presenters for today, and we will get going. Our first presenter is Raj. I've known Raj for many years. He's the CTO and co-founder of ClearFunnel, which is a company that does data analytics and provides services for a number of organizations, both large and small, all sizes. It has been a successful startup a couple of years back, and it's now growing very quickly. They do use HPCC across the board, as you can imagine, and that makes it very relevant to this session. And he will tell us how he used HPCC to get this successful company off the ground and now doing things that many other companies have dreamed for a long time. Before I give the floor to Raj, I want to introduce our two other speakers today. There is certainly Bob Foreman, who you already heard, and he's now taking over for Jessica for just temporarily until Jessica comes back. And he will be talking about of course, he doesn't need more introduction. He will be talking about some interesting capabilities of ECL, and since yesterday was Valentine's Day, he will be giving you some ideas around relational models in HPCC. And James, who will talk before Bob, will be covering new plugin, and this is an enhancement over what we had before. This allows access to Hdfs file systems, but in a way that is fully distributed. So it's essentially node-to-node, and that opens the door to integration with Spark and other platforms out there that leverage Hdfs. James has been with us for some time, like Nexus. He's one of our software engineers, and has been working on enhancing HPCC among a number of other tasks over the last several months or years. And I think you will find all of these talks quite entertaining. Again, the first one is Raj talking about ClearFunnel and the way they use HPCC. The next one is James talking about Hdfs integration with a new plugin. And last but not least is Bob talking about relational databases on ECL. And without more preamble, I will give the floor to Raj. Hello, Raj, and welcome.
Thank you, Flavio, for that excellent introduction. You've been too generous, I should say. Thank you all, guys. I'm honored to be your speaker today on this HPCC Tech Talk. Before I jump on to my presentation, which is going to be scaling data science capabilities, you should be seeing a poll in your screens presently. If you can take a moment to answer that, that will be helpful. Where have you had the most success in deployment of HPCC systems-based solution? You should see all the answers below. Choose one, and while you're looking into it, let me jump into my presentation. What I'm going to talk today is about when we started ClearFunnel, we thought that we wanted to be a big data science analytics company. And if you wanted to be a true data science company, what do we need? And we found out that we need not just data science capabilities, which is machine learning and artificial intelligence. We also need big data processing, cloud, so that I can scale because we are a startup. And lastly, we should be able to do it with least cost. So these were the things we were thinking. And we were worried whether will we be constrained if we do all of this to only go after some domains and not all domains. And we are going to show you that how we could go with a variety of problems that we could solve just by these simple tenets. If you're talking big data processing, we all know that the top of the list is Hadoop and Spark. Right? This is the most widely known story of big data processing is MapReduce. We all know it started with MapReduce, but MapReduce had some minor challenges which needs to be solved. So then came along Spark, which avoided a lot of problems with read and write by keeping the data in memory. And it also introduced something cool, directed acyclic graph, which allowed basically to process and navigate a graph, but with one small caveat, right? The graph data should not have any circular reference. And then there were a lot of people which did incremental innovation. They did Solar, they did Pig, HBase, Hive, and you also started getting support for Java, R, Scala, etc. And so which means a lot of integration, but this is a talk about HPCC. Why am I starting with Spark and Hadoop and Pig and Hive and other ecosystems? Because whatever I said today needs a lot of engineering talent, except this was already version 1.01 in HPCC systems. So we said, okay, if this is the case, let us take the original, the grandfather of all of this as HPCC systems and use that as our big data processing engine. So that is our first checkbox. Can I use HPCC for a big data processing engine? Answer is yes, because it gives me the capability of all the other systems which I talked about. Once I go into big data processing, the next step for me is machine learning and artificial intelligence. Well, let's face it, right? Machine learning is not new. It's been there for what, 25, 30 years at least. And usually people use R for machine learning, and now Python has been the most widely used language here. Now Spark started offering support for these languages, which looked like as though you would get scale with it. But there was only one small problem, that the R and the Python constructs now need to conform to the Spark paradigm before the existing code would be written, would be successfully executed on this Spark cluster. So that is the first problem we faced. The second problem we faced, there are a lot of I would say that Python is basically a middle tier scripting language, but it was retrofitted with object-oriented paradigm capabilities, and now people are trying to do complex data manipulation, transformation and computation with Python, because now Python and Spark are integrated. This is the problem today with machine learning when you are trying to do it in scale. But at the same time, there were also HPCC systems which is trying to do machine learning on their own, because one of the things is HPCC system starts with a fully parallel construct. All their modules are fully parallel. When they try to do any data operation, they try to see, can I distribute it across all my clusters? This is the first start they do. With this, they started building up supervised and unsupervised models, and using just ECL libraries, how can I start building multiple machine learning models, including neural networks and deep learning? This is the journey which HPCC is currently undertaking. So when we looked at these both, we said, hey, we want to use the data science capability. We don't want to get stuck back into the constructs of Spark, MapReduce, or the key value pair. And what do? So we just took HPCC's capabilities and we started adding stuff to our own ECL machine learning. This is one of the small things we had to do when we had to bring in machine learning into data science. Hopefully in a year or so, with all the new releases that HPCC is coming up, most of what we have done would become part of the open source system. One of the things we did, just to talk, make it interesting, is we have done text processing libraries in ECL. It's not just entity extraction or semantic sentiment analysis. We now do context analysis. We do point of view scoring. We come up with a layered taxonomy which would take you and make you understand how to do and analyze text in a holistic way. We have done image recognition in ECL libraries. We have done pattern matching for both OCR based as well as neural network based, just by extending and writing ECL libraries. We have also done geospatial analytics used for a maritime domain. We had to do a maritime predictive analytics, and we took the data and started understanding geospatial data and how to do predictive analytics with IoT screening. So with this, we said, okay, we are set for not only big data processing and also data science. Now this is great. Now you need scale. You don't want to invest in hardware, and everyone knows that cloud is the place to go. Now cloud has become table stakes. We don't need to worry about anything else. If you do not have a cloud version, then you are not considered having a scalable product at all today. And the biggest advantage we got, HPCC systems out of the box in their open source version started providing native support for AWS. When I say native support, all I'm talking about is a one-click deployment. You click, your AWS has your HPCC systems, and it is done. And HPCC systems is a very homogeneous stack. But one of the main things for me when I considered why we had to go with HPCC and AWS is, when you want to go to AWS, you don't want to be bogged down with a lot of other containers and tools and stuff. Like for example, you don't need to be a Docker or a Kubernetes expert to set up HPCC systems on AWS. AWS has really scaled for two of their core competencies, which is their EC2 and S3. When you try to see how AWS is making money, it's about their processing time and storage using EC2 and S3. Everything else has been layered on top of these two. Now when we found out that HPCC is directly leveraging EC2 and there is no additional containers that we need to worry about, it was a no-brainer to fit AWS into HPCC and say this is what we will do. But this was not just enough for us. We wanted to take it further to scale. We wanted to make sure that all the IOs and other scalability which we need between AWS S3 and the HPCC cluster has to be faster than what we were doing with MapReduce and AWS accelerators. So we started writing some connectors where we can spray and despray your data directly from S3 into EC2 in a much better way, more than what Netisa could do. So we started doing some tests. We did tests and found out that we could do up to 2 terabytes easily without even worrying about it. We know that with whatever limited resource we got, right, if we can achieve this 2 terabytes, we are there. And that is a lot of IO speed, which can significantly provide advantage for processing terabytes of big data. Not only that, the next thing we wanted was micro-batching. Why am I talking about micro-batching? HPCC, if at all there is a challenge which people say is it is not good for real-time processing or near real-time processing. But for us, we wanted that near real-time processing to be shown so that we can get more commercial solutions out of our platform. So we said, let's start talking about micro-batching. How can we do micro-batching? We did a lot of tests trying to see how to leverage the native hooks provided by ECL and the microservices of the AWS cloud and start looking at the size of my batch. We did a lot of extensive tests in our laboratory. We wanted to make sure that the capability included automated roll-up of the sub-indices, coordinated housekeeping of the super files and the dependent sub-files, and how to do a hot swap of the new index version with zero downtime. With all these tests, we found out that with the 10-second interval for analytics is an amazing updatable outcome and acceptable outcome for our client businesses. If it is in less than 10 seconds, the cost is not that viable for us. But if we found that if we can keep it in sync, all the clusters and indices within 10 seconds, we found out that it's an amazing solution for us to do micro-batching. So what we do basically, we said that let's make sure we set up micro-batching every 10 to 15 seconds update so that it is cost effective for us and it does continuous operation of HPCC without introducing any new technology. Then what we did was we took our results and then we formed a lookup table which maps what is your delta index size to the optimal micro-batching frequency. Now we have automated this reference table in our platform. So what happens is when we look at the size of the data, when we look at what will be the index size that will happen, it automatically decides the micro-batch size and it comes up with not less than 10 seconds and as high as needed. So what happens is every size of index in each micro-batch dynamically is determined for the optimal wait time before the hot swapping can happen. This avoids race condition, no other micro-batching issues for us, and for the user, you still have the sub-second response time serviceability using Roxy, because all we know that Roxy is highly concurrent, low latency queries. So we wanted to make sure that is not affected, and we came up with the micro-batching. And lastly, we wanted to see that if there is any failure that is happening, that can be instantaneously recovered. We don't want to start the graph again. We know that the graph, the way we process HPCC is the key to understanding how HPCC is done. So at any given time, we wanted to make sure what are all the graphs that have been completed, we want to keep it, and the data is parsed along clusters. Again, so we leveraged our knowledge of HPCC to S3 connectors to make sure that this job failure operation is smoothly handled. So that gave us, hey, we have all the capabilities of big data, data science, and cloud. And before I move on to the next slide, I just want to summarize. When you try this, you have to understand only two things, right? Key principles. Do not look for any additional big tools and other layers to make it happen. Keep it pretty simple. Keep the abstractions to the lowest level so that you don't start adding much layers to it. And do not forget that HPCC systems has no fluff. AWS EC2 and S3 has no fluff. Try to marry them directly rather than going through additional containers. That is the three principles we follow to make it successful. Now that we got the big data, we got the cloud capability, and we got the machine learning, we turned our attention to all the different areas we can work on. Very surprisingly, these are some of the complex data engineering use cases we have solved today in ClearFunnel using the platform, the just HPCC and AWS. Complex and large graph traversal across nodes, image analytics. I know that we saw a couple of image analytics as a part of our HPCC conferences, but that is only scratching the surface. There is a lot more we can do with HPCC in just image analytics. We have done pattern detection and anomaly detection for bioinformatics for gene processing. Text analytics, we have taken it beyond entity recognition and just leveraging the semantic part of it. We have gone into point of view support scoring. We have gone into context understanding, analysis, etc. Advanced search and querying. This is another thing. We have found out that HPCC could actually be a very direct implementation for advanced searching and querying if you can do a transformation of the data in one particular way. Because the Roxy has been so finely tuned, we found out that with the micro-batching, with the incremental index, with the super key concept, we can actually make Roxy to be a near real-time search query engine by itself. And there are people who wanted to have the petabytes of data put in so that they can search faster. That's all the things they want. And HPCC as a very simple system ground up, we could make it happen in a matter of a handful of weeks rather than doing months of development. And lastly, it is a single homogeneous stack. Why we are saying this is a single homogeneous stack? Because of the general purpose nature and suitability of ECL, right? This was a key aspect to us. And I want to tell this once more, right? One of our clients' use case required extreme graph traversal at one specific step of an overall analytics pipeline which we were building. They need to do it recursively mine a graph of several 100 billion nodes and vertices, and it needs to go very deep. Quickly, it has to go very, very deep. The solution was similar to one like a Dijkstra algorithm you provide, right? But we were able to do it with just ground up ECL. The reason why we are doing it is not that we are comparing ECL's performance with already available graph traversal solution, but ECL is a general purpose language that, hey, when we found out this scenario of graph traversal, we need not look for a new solution, but just leverage ECL and the Thor Roxy capability of the distributed computing and low latency querying capability to build it, and instead of going for a dedicated graph database and learning new programming skills, we just did it with our system. And let's not forget, guys, engineering talent is the most important one. You wanted to make sure that you have a homogeneous stack because your engineering talent needs to be less, because the cost of operation trying to get costly resources for your startup is one of the biggest things that can happen. We are all, some of you are startups here, some of you are endeavoring to be a startup. We know that we are going to start with a core set of people. When you have a core set of people, you don't want to distribute them across multiple technologies. That is one of the biggest advantage we got. And because you know the number of lines of code a programmer can write in a day has been fixed. There are a lot of studies about it before the fatigue sets in. You want to make sure they write the least amount of code. And ECL being a declarative language is much, much suitable for productivity, so that people start focusing on functionality rather than trying to optimize the work they have written over and over above again, because you need to fail fast. You need to fail often. You cannot afford to take a lot of time to polish a diamond and come out and see that there is no market for the diamond. Lastly, our dedicated support staff, right? We are not having a cloud engineer, infrastructure engineer, network engineer, or a production support person or a DevOps person. And we don't have much R&D engineers on HPCC also. Let's face it, right? Our work is in core ECL and Thor and Roxy operations. When we are doing it, we directly reach out to the HPCC core team. Since it is not one of those integration layers and it is core HPCC and ECL, we get phenomenal support and response from the HPCC team, because it's either a core capability of the product or what we are asking for is a direct enhancement to the core product. So automatically we get one of the best support that is possible from the HPCC team. This has let us come up with our platform in a very cost-effective manner, in a fail-safe manner, with a smaller headcount of resources, so that we are not worried about attrition and more people coming in, and has made us go across multiple domains of the work, not just text or numerical analytics, which many people do, but into more areas like image processing, and currently we are trying to work on acoustic analytics. So most probably, if we are successful, we will be giving a chat on that. So that's how I will be wrapping up my presentation on how we built the data science capabilities, and using just a single homogeneous big data ecosystem, and how we were successful in doing it across multiple commercial domains. You should be seeing a poll now in your screen. Please answer your poll, and we will start taking some questions.
Raj, thank you. I wish Bright Talk had an applause button, because that was a wonderful presentation. Thank you again, sir. And let me look at the first poll question. And while we do that, Raj, if you look at the questions from the audience, there's a couple there in the queue. You might want to take a look and prioritize which one, and we'll get to that in just a moment. The first poll result, where have you had the most success in deployment of HPCC systems-based solutions? Over half of you, 54%, use on-premises infrastructure, 27% of you are on the cloud, and 18% have a hybrid deployment. So let's take a look at some questions here. The first question for you, Raj, how does HPCC systems handle micro-batching for real-time analytics requirements?
So this is something which we have written as a library extension on top of HPCC's open source. Basically what we did was we leveraged the super index super key format and said how can we make sure that we extend it such that it does a micro batching. So it is both size versus time constraint, right? The way we wrote this is in how soon can we do it and with how often should we need to do it, with what should be the size in which we should do it. And it did amazingly. Like I said, if we wanted to do less than 10 seconds, we found out that it doesn't scale well because of the inherent nature of how the data has to transfer from Tor to Roxy and how the indices should need to be moved. So that moment when we are talking about large sets of data, we found out that it is taking some time. So therefore, we came up with the lookup table of how to make sure that the size data versus the time is done. And we found out that if it is more than 10 seconds, we can actually handle terabytes of data in an adequate manner.
All right, thank you. Our next question coming in is the work done for rolling updates open source as well? If so, where can I find the code?
The rolling updates is not open source. It is ClearFunnel proprietary. But the basis on which we wrote on it, the rolling updates, is part of the core HPCC competency. So, Bob, I think you yourself have taken classes for me on how to do the super key index and the rolling updates within the HPCC capability. That is part of HPCC, so it should be handled in a normal class. We can see it actually there, and the code is there in the open source for the basic underlayer on which this micro batching rolling update has been written.
Excellent. Yeah, got it. So the super keys, you can update the sub keys while the query is active, and also use package maps to help with the deployment, so the query never has to come down. All right, very good. Let's do. We've got a few more here, but we've got time for maybe one more. I guess, Trish, unless you want me to continue. Regarding deep learning with geospatial, is there any specific library for geospatial functions?
No, we are using the same functions which are already available in HPCC library. We have extended it. The main thing we need to understand is geospatial data is latitude, longitude as a unit, like a point, right? What we say in Java or Python. So we took that data and we understood how that data works, and we have written our own small libraries for Great Circle Mapper and other latitude, longitude, geospatial functions which are available in open source in C++ or Python or Java. We just adapted it for ECM.
Okay, and let's see, we have time for one more, and I think Raj, I think also for image processing, you're taking advantage of the image processing libraries of HPCC, or is that your own again?
We started using the basics of image processing with the HPCC. The way they solve the matrix, way they solve the distributed matrix algorithms, because the basis of image processing is your matrix operation, which we all know, right? MATLAB used to do an amazing job, but the MATLAB's biggest problem is that MCDS is not that good. Whereas in HPCC, when I try to do similar stuff, I get phenomenal response and I can scale it as much as possible for free. Whereas MCDS, I need to pay more for more licenses and more scaling. So we have taken that capability and we have built additional stuff on image processing.
All right, thank you, sir. And just one more question, then, if I can squeeze this in. and this may be a long question. You may want to answer this later, but primarily it says, have you needed to implement stream processing to deal with IoT-based requirements? And if so, can you explain how you implemented it?
I will keep it to 30 seconds and give two hints. One is streaming into S3, second is micro batching. So these are the two biggest changes that is required. Very simple, if you can understand how to stream it into a landing zone continuously using any open source version or bring it into S3, doesn't matter. And then do micro batching, which we discussed earlier in the webinar. That should be more than adequate to satisfy any IoT processing. The only thing you cannot get is instantaneous complex event processing responses, but those are not the use cases which we are working on today anyway.
All right. All right, thank you, Raj. That's great. Trish, let's see here. I'm trying to look for the second poll, and I don't see it in that list. So is there something I need to do with that to review those results?
Hey, Bob, it should be there. Just click the votes from audience, and you'll see the results.
Let's see. I've got the first one, but I don't see the second one. I have the one with the most success in deployment of HPCC systems, but I don't see the second poll popping up.
It's okay. I can share those results with everybody. It came in loud and clear that, in your opinion, which of these use cases are most suitable for implementing an HPCC system? 70% were all the above. So in all of those areas, in numerical calculations, text processing, image recognition, and voice analysis.
All right.
So
thank you so much. All right.
Welcome.
Thank you, Trish. And all right, we're going to move on to our next presenter. And again, this is a good one as well. Something interesting I think a lot of people have had questions about in our training classes, the Hdfs connector preview. And again, I want to introduce you to James McMullen, who's our software engineer at LexisNexis Risk Solutions. James, take it away.
All right, thank you, Bob. So as Bob mentioned, I'm going to be talking today about an in-progress HPCC to Hdfs connector. And I'm sure all of you are familiar with Hdfs. All right, so before we get started, I would like to do a quick poll. How many of you are interested in interacting with Hadoop, the Hadoop ecosystem from HPC systems? And I hope that's a good number of you, because that's essentially what we're going to be talking about today. All right, and the results of this poll will be shared at the end of the presentation. All right, so a quick overview. Integrating HDFS and HPCC is a pretty big topic, so there are three main topics that I'd like to cover today. The first topic being the motivation and goals behind creating the HDFS connector. And then a brief overview of the architecture of HDFS. This is going to be important for us to understand some of the design goals and the design of the HDFS connector itself. In particular, we're interested in how data is stored in HDFS and how we can read and write data to and from HDFS. Finally, an overview of the HDFS connector itself and its design, with a focus on how it achieves parallelism. And at the end of the presentation, a quick demo of the in-progress connector itself. All right, so starting with our motivations, why are we creating this connector? As both Bob and Flavio have just mentioned, we have users that are wanting to interact with Hadoop and HDFS datasets. So that could be existing HDFS datasets in Hadoop, or it could be applications built on top of the Hadoop ecosystems. That could be Spark or just MapReduce applications. And in the past, we've been able to fulfill these requests through the HPCC to Hadoop project or H2H project. Unfortunately, the H2H project is no longer being actively maintained and developed. So our primary goal is to step in and fill that gap left by the H2H project and meet the needs of our user base. There's also a chance to improve upon the H2H project. When the H2H project was started back in 2012, there were a different set of obstacles and constraints than there are today. This opens up the possibility to learn from the H2H connector and improve upon its design. There's also the possibility to add new features, such as variable record length support that wasn't available in the H2H project, and the possibility of adding in Hadoop-specific file formats. However, at the moment, we're going to be focusing only on CSV files and DOR files. All right, so when we start a project, it's really important to have a set of guiding principles and goals. Otherwise, we would most likely fall short of what's possible. So to kind of start with, I want to talk a little bit about what our goals and guiding principles are. Our first guiding principle is robustness. The connector itself should just work. If the connector does not work reliably, it doesn't matter how feature-rich or performant it is. No one will use it. Expanding out this goes more concrete principles. We want the design of the system to be as straightforward as possible. We want the final connector to work as closely to the ideal scenario of streaming data directly from Hdfs into an in-memory HPC dataset as possible. The connector should also have as few dependencies as possible. These dependencies could be libraries or external systems that must work in concert with the connector. And these are just extra failure points, essentially. And finally, the connector should have little to no configuration required to get it to work. We would also like the HDFS connector to be as tightly integrated as possible. And by tightly integrated, I mean when we interact with the data set from HDFS, it should be as similar to interacting with the data set from HPCC as possible. In short, HDFS data sets should be first-class citizens. Finally, the connector should be performant. In particular, we want to utilize the full capabilities of the HPCC cluster when working with HDFS datasets. Therefore, datasets should be able to be accessed and transformed in a distributed manner. We should also seek to reduce the data transfer costs and streaming data from HDFS to HPCC. So, again, as I said earlier, it's probably important to have a good understanding of the HDFS architecture before we kind of get into the design of the connector and how it works. So that's where I'm going to be starting. And this is, again, a pretty big topic. So I'm going to be focusing on a few aspects of HDFS and its architecture that influence the design of the connector. In particular, we are interested in how HDFS stores and retrieves data. So jumping right in order to attain scalability and reliability, HDFS breaks files down into blocks of data and file metadata. File metadata is everything from permissions to where a file is stored. And data blocks are the raw data segments of a file and a checksum of that segment. These blocks are usually 64 megabytes in size and are replicated across the entire HDFS cluster to provide fault tolerance. I really shouldn't have said entire. It's generally 3 copies per block or so. As an example, if we have a 1 gigabyte file, the file is broken down into 16 blocks of data, and then multiple copies of each block would be distributed across the HDFS cluster. HDFS breaks down the responsibility of storing this data within the cluster between 2 types of nodes, the name node and data nodes. Data nodes store blocks of data but have no concept of files. The name node stores file metadata for each file, the file system hierarchy, and the location of data blocks within the cluster. And as a note here, the name node can be a single point of failure. And there are some things in Hadoop to mitigate this risk, but it is something to be aware of. All right. So we talked a little bit about how data is stored within HDFS. So how do we go about reading and writing data from HDFS? So the name node acts as an arbitrator for reading and writing of files. So if we're a client and we want to read data from a file in HDFS, we would first contact the name node and ask for access to the data that we need. The name node would then authenticate and authorize us, and then returns a list of data nodes that have the block of data that we need. We would then request the relevant block of data from one of the data nodes directly. And you can kind of see an example of this process in that diagram on the top right. We have 2 client applications on the bottom that are reading data. The client application on the left is just starting the process, and it's talking to the name node, and the name node responds back with a list of the data nodes that have the data it needs. It can then directly talk to the data nodes and start streaming that data. All right, so writing follows a similar pattern. We first contact the name node and tell it we would like to write to a file. The name node then checks to see if that file is available for writing. The primary reason a file would not be available for writing is it's locked by some other application that's currently writing to the file. On the client side, we buffer data until we have a full data block and then ask the name node where we can write the file to, and this would be one of the data nodes in the cluster. We continue this process until we've written out the entire file. An important takeaway about writing files is that HDFS supports multiple simultaneous readers, but only one writer for a given file, one writer at a time for a given file. So this is a fairly involved process. It's not the hardest thing, but definitely not something that we want to have to implement ourselves. Luckily, Hadoop provides libraries that abstract away this process of reading and writing files behind a file system API. So while we don't have to implement these processes ourselves, it's important to understand how they work and what's actually going on behind the scenes, and that's going to help inform us when we're developing or in designing the HDFS connector. Another item to note is these libraries that HDFS provides to abstract away this process uses Google protocol buffers internally. And it's using Google protocol buffers to define messages that get sent between the name node, the client, and data nodes. And so it's completely possible to take those Google protocol buffer definitions and make our own implementation of this protocol, of this reading and writing protocol. However, that would still be a lot of work, but having those Google protocol buffer definitions makes it at least possible. All right. So we've talked a good bit about how HDFS works internally, but how do we go about interacting with HDFS? The most obvious choice is just use the Java, Hadoop, or native libHDFS libraries that Hadoop provides within the installation itself. However, there are a couple of caveats to using these libraries. The first of which is they require Hadoop to be installed locally, or at least the majority of Hadoop. Hadoop doesn't necessarily have to be running, but it must be installed. Another item to note is that while the libHDFS library is a native C library, it's a wrapper around the Java Hadoop libraries. So either way with Hadoop, we have to have, with the Hadoop libraries, we have to have Hadoop installed, or at least most of it, and we also have some overhead of moving data across a JNI boundary, the Java Native Interface boundary. So there's going to be a couple of downsides to using the Java libraries, Java Hadoop libraries or the libHDFS library, and that being that we have to have Hadoop installed, and we have a little bit of data transfer costs due to the JNI boundary. So as I mentioned in the previous slide, both of these libraries internally use Google protocol buffers. So if we wanted to, we could use Hadoop's protobuf definitions and communicate with HDFS directly. And again, this is possible, but it represents a significant amount of work. So a third option, and the option we ended up using, is actually another library, libHDFS3, which is part of the Apache Hawk project. And if you're not familiar with the Apache Hawk project, it's a SQL query engine built on top of Hadoop that allows you to manipulate and query HDFS datasets. And the interesting thing about libHDFS3 is it's a completely native implementation of the libHDFS API using the Google protocol buffer definitions in Hadoop. So it's completely API compatible with the libHDFS libraries, but it does not require Java Hadoop to be installed. And so this is actually what we ended up using. And the nice thing is, since it's API compatible, we could actually swap this out at runtime, or we could even statically link libHDFS3 and completely remove all dependencies on our plugin. And that's actually what we ended up doing. All right, so we talked a lot about how HDFS works and how we can communicate with HDFS, but we haven't really talked too much about the HPC side of things. So how do we handle interacting with HPCC? How do we integrate our new plugin? And there are a couple of different options that we have, and the biggest thing here is we're trying to figure out what is the best way to read in this data in a distributed manner and with the least data transfer cost. So we could use ECL pipe. It's a built-in ECL action. That's actually what the original H2H connector used. And if you aren't familiar with ECL pipe, it executes a shell command locally on each node in the HPCC cluster. Data sets are then written and read via standard in and standard out to that application. So the biggest advantage to using something like ECL pipe is that it's built in, it's native, it's ECL. We don't have to worry about the distribution. It's automatically handled for us. However, it's loosely coupled, so it adds a potential failure point, and it also comes with a pretty high data transfer cost due to how it reads and writes data through standard in and standard out. Another option is that and the first thing that we actually tried was using HPC's Java import feature to access the Hadoop library directly from ECL. And this method worked, but it had a few downsides, the primary of which is it's difficult to implement parallelism. The Java import feature does not have a way to specify that a function should be run in a distributed manner. So while we could find some workarounds for this, and we were able to, they came at some costs, some performance costs, and had the potential to bubble up the complexity to end users. So this kind of violates a couple of our stated goals and guiding principles. Mainly, we don't want to increase the complexity for end users. So that was kind of a dead avenue. But it actually did lead us to the correct solution, or our final solution, which was to create our own ECL plugin, just like the Java implementation. So the Java implementation is actually a Java embed ECL plugin. It's a native shared library that gets added throughout the HPCC cluster, and this allows you to pull in Java libraries via the JNI. So we have the option of creating an ECL plugin that would do that for us. The interesting thing is it embeds, so the embed definition inside of ECL allows you to specify that an embed should be run in a distributed manner. So as an example, if you're embedding R or JavaScript into ECL, you can specify that that should be run in a distributed manner such that each node in the HPC cluster is going to run that code independently. And so if we define our own ECL plugin that has its own Hdfs language, we can then specify that any actions that we expose to ECL will be run in a distributed manner as well. So this is our the overall solution. And another nice thing about creating an ECL plugin, a native ECL plugin, is that it allows us to write directly into an HPCC data set. So that really lowers the cost of transferring data from Hdfs to HPCC. All right. So I've talked a good bit about how we interact with Hadoop, or Hdfs, how we interact with HPCC, and how we communicate between the two. But I haven't really talked at all about reading or writing of files. And while those other topics are pretty big in and of themselves, you know, reading and writing is kind of what we're here about. So how do we read files? So there are kind of two different scenarios that we're supporting at the moment: CSV files and flat files with a fixed record length, and variable record flat files. So reading CSV files and flat files with a fixed record length in a distributed manner is pretty straightforward. We essentially break down a file in Hdfs into logical chunks, one chunk for each node in the HPCC cluster. Each node in the HPCC cluster is then responsible for loading the records from its chunk of data. An issue that arises from this method is that the chunks would not be aligned to the beginning of the record. In HPCC, that's actually not the case, and the file parts does that automatically for us. That's nice, but with Hdfs, we don't get that advantage. So we run into the scenario where we have a record that starts in one chunk and ends in another. And you can see that up there in the diagram on the top right, that orange rectangle is a record, and it starts in the chunk before our chunk and ends in our chunk. So that's no good. So the solution to this problem is to load all the records that begin in our chunk, not necessarily that are part of that overlap our chunk, but only the records that begin in our chunk. So in order to do this, we scan forward within a chunk until we find the first record and begin consuming records from there. This also implies that we will need to read past the end of our chunk to consume the last record. And you can kind of see that last record hangs off the end of our chunk in the top right. So this works in the case of a CSV file and a flat file because we can scan forward to find the carriage return character inside of the CSV file. And on a flat file with a fixed record length, we know that a new record begins every X bytes. So we can identify the beginning of records. The problem comes in with variable length records. We have no way to determine where a new record will begin just based upon the data as we look at it. So there are a couple of options that we have. We can attempt to, we need basically more data to be able to process this in parallel. And essentially we need to know to at least where at least one record per chunk begins. So we have a couple options. We can pre-process data sets and export split metadata that we can then use to process these variable record lengths, record flat files in parallel. And you know, so this can either be a pre-process step, or we can actually create this split metadata on write. If there isn't, if the split metadata does not already exist, we would use the pre-process step. And if we are actually writing out the data, we would just write out the split metadata as well. And so you can kind of see in the bottom what I'm talking about. We have this chunk of data, and somewhere in here a record is going to begin, but we can't really tell where. We know that we have records in there that we want to read. So if we add the split metadata information in, we can find records in here. Now we're not going to create a split for each record in the data set, because if we have a billion records, that'd be a billion splits. What we really want is we want one split or a couple of splits per node. And choosing the number of splits is kind of a, an optimization question. And we can look at the size of the data blocks in Hdfs and the number of nodes in HPCC to determine how many splits we actually want. All right. So we talked about how we can read files in parallel. Writing files in parallel also presents some interesting challenges. Our data sets in HPC systems are distributed across the nodes of the cluster. However, writing a file in Hdfs is a single writer mechanism, as we discussed earlier. So if we want to write an entire data set to a single file in Hdfs, we would need to do so sequentially. Unfortunately, this means we would need some sort of synchronization primitive to control when each node of the HPCC cluster should write. Because again, we were able to have our plugin execute in a distributed manner. So we need some way to now synchronize and write to this file sequentially. Unfortunately, there's no good mechanism exposed through the ECL plugin API to implement this. So our solution is to create a temporary sync file in Hdfs that acts as a synchronization primitive. After each node is finished writing, it writes the number of the next node to that sync file so that it can check the file and then begin writing itself. This process continues until all the HPCC nodes have written to the dataset file and the file has been closed. So this method also requires some configuration on the Hdfs cluster side. You have to enable an append mode because essentially we're just appending to the file one at a time from each HPC node. So another option, and this is very similar to how HPCC stores files, is to create multiple files, one for each HPCC node. And this is very familiar, similar to how HPCC breaks down files into multiple file parts. This method will allow for parallel writing, but also means that whatever application reads the data set would also have to be aware that the data set is broken up across multiple file parts. So while a multiple file part solution is definitely the preferred solution, we provide both methods to end users. This allows existing Hadoop applications to use HPCC created data sets without having to be updated, while at the same time allowing an optimized pipeline for applications that can support it. All right, so now I want to give a quick demo of actually using the HDFS connector to read and write data sets. So hopefully this will work. Bear with me, I'm going to try and share my screen here. All right, that should be coming up, and hopefully you can see that now. Excellent. So first I want to talk a little bit about the setup here that we're testing on. Basically, I've got 3 virtual machines running with Hadoop and HPCC installed in each. So we have a master and 2 slaves. And so I have ECL Playground up for HPCC here. And you can see that we're importing this library called HDFs, and that's actually our native ECL plugin. And this ECL plugin exposes 2 different actions. An HDataset action, and the HDataset action is going to be reading a data set from HDFS. And you can see the connection string here. And so it's a pretty simple, pretty standard HDFS connection string. We've got the name node and its port, and we can actually come over here to our Hadoop web interface here and get that name node and port. And then we've got a file location and then the actual data set that we want to write out. And so if we come over here, so we're in user HD user, there's currently no file here, all right, because we haven't written anything yet. And we're also passing the record here. And so this is loading data in, right? And so we'd pass in the record structure for the file that we're wanting to pull in. We've also got the HOutput function, which takes a data set to write and then another connection string where it should be written. It also takes the record structure as well, and that's so that we can generate that split metadata and generate other metadata and save that to HDFS as well. All right, so a quick demonstration of this working. We're going to generate a data set. And this is going to be the same code that was used in the Spark and HPCC benchmarks back in the fall. Essentially, we're just generating a really small data set, 250,000 entries, It's a key value pair, so we've got an integer key and an integer fill. And we're limiting the unique keys to 10,000 keys, or 100,000 keys, I'm sorry, and 10,000 unique fills. And we're going to generate this in a distributed manner, and then we're just going to output this to the Hdfs cluster. All right, let's go ahead and run this. All right, so that completed, and we can see that it wrote 250,000 records. That's good. So if we come over to Hdfs here, all right, so we've got this benchmark integer DS data set. It's exactly what we're looking for, and you can see the sync file's already been deleted. All right, so let's go ahead and take a look at what that file looks like. So we're going to go ahead and read it via Hdataset. All right, and as you can see, we've got a key and a fill, and we've got 250,000 records. So that's a full round trip. That's pretty good. All right, so let's actually do some transformation on this data. I'm going to go ahead and just sort it. And again, this is one of the tests that we did as part of that Spark and HPCC benchmark. All right, so we're just going to pull in the data set via the Hdataset action here, sort it, and then write it back out. And we're going to write it back out to a new data set sorted DS there. All right, so run this. All right, it's completed. And we've got a new sorted data set. All right, so let's take a look at what that the new sorted data set looks like, and hopefully it'll be nice and sorted for us. Or when we're sorting on the key there. All right, so let's change that to sorted real quick, if I could type. All right, so that's completed, and as you can see, it's actually sorted our data set just as we expected. Go to the end here. All right, so we've got a nice sorted data set. So it's pretty straightforward, and again, our goal was to make this as tightly integrated with HPCC as possible, and I think we've achieved that. All right, so I'm going to stop sharing my screen here. All right. So going through my backup slides there. So a quick poll for you guys while we're getting to the questions. Do you currently use Hdfs as a data store? And I hope at least some of you do or would like to.
All right, James. I think that's it. Is that it for your slides? Is that good?
Yes. Yes, that is
yep.
it.
Okay. Yep. All right. So yeah, do you currently use Hdfs as a data store? Go ahead and answer that poll. Let's look at the results for the first one. And the first question was, would you be interested in interacting with the Hadoop ecosystem from HPCC systems? And we have a tie. We have 50% yes, 50% no. So, of course, we could have used some more voters on that one, I think, but let's move on to the next one. And let's look at the questions from the audience as well. And right on the top, we'll start with that one, James. I see this as being a very useful tool for the community. When did you say it would be available?
That's a great question. I didn't, unfortunately. It's still in progress. I can't quite give a timeline. However, it will be available on the company GitHub when it is complete. Hopefully that'll be sometime soon.
All right, thank you. Next question, did you test performance? Does performance really scale with the number of HPCC and Hdfs nodes?
We're still testing performance. It does scale, so this is still running in a distributed manner. Can't quite say how that compares to a native HPCC data set. We do know it will be lower because there's extra transfer costs of going over the network, et cetera.
All right, and we have one more question. Does this work for writes to Hdfs2? I think you might have answered that in your presentation, but does this work for writes to Hdfs2?
Yes, it does, and hopefully that demo kind of demonstrated that as well.
All right, fantastic. All right, thank you, James. And we have one more poll. Let's just take a look at that. Still coming in. We have eight votes now. Do you currently use Hdfs as a data store? Well, 62% said no, and the other 37% said no, but I would like to. So there you have it. All right, so fantastic. I mean, to give us an awareness of what's available out there and the possibility of using Hdfs connector in the future. That's a really good thing. So, all right, James, thank you so much. We're going to move right into the last presentation, and yours truly will be presenting. Again, my name is Bob Foreman, and I'm a senior software engineer at LexusNexus Risk Solutions. And, well, when I first was asked to do this, we wanted to do a Valentine's Day special. So I decided, I was thinking relationships, and I said, well, I just was finishing an advanced ECL class, and I said, well, let me give, a lot of people go to the introduction class and then they drop out and don't attend the advanced class for time and other issues. But I wanted to give you kind of a glimpse of what we do in the advanced ECL class. And so we're going to be talking about relational data sets in this next section. And if we run out of time, I don't know, I was talking to Trish, we might extend this to a part 2 in next month's Tech Talk, or if I can't get my screen share to behave, we were doing a dry run earlier and we had trouble getting it up. So the ECL demonstration might have to be on hold until next month. We'll wait and see on that. So first of all, let's talk about the quick poll. Have you ever worked with a relational denormalized data set in ECL? And while you're thinking about that, let's talk about why you would want to do something like that. First of all, a little background. Most of our data sets in the LexusNexus community on an HPCC cluster are organized in a normalized architecture. And Database 101, normally that means that one data set can join with other data sets using a unique linking field in a one-to-one or one-to-many relationship. And on LexusNexus, we affectionately, I think actually David Bayless, our chief data architect, named this. He calls this architecture the data donut. And some of you may have seen this slide. I first saw this actually on social media. Thought it was pretty cool. This is called the LexusNexus Data Donut, where the center of the donut, of course, is a base file, they call it a base file or an authority file, and those identifiers there were just different nomenclature or terms that we use to identify these unique identifiers. Surrounding the donut are all kinds of related entities, everything from property to vehicles to relationships, banking information, email information, etc., etc. So the problem is sometimes when a customer wants to know everything about a particular business or person, it becomes problematic to analyze these normalized data sets, to pull them all together into one cohesive output. And a lot of times people try to tackle it with using a series of joins. Join the base file with this file and then take that result and join it with something else and join it with something else. So the concept of denormalized data sets solves a couple of interesting problems that normalization can sometimes bring forward. So in our training class, we talk about an example hierarchical relational database. We talk with people, and one person can have 0 to up to, I think in our training set, we'd have 20 vehicles. And so there's a parent-child relationship between people and vehicle. We have a parent-child relationship between people and property. And then even a piece of property can have multiple tax data information year by year, so we can keep track of how the property is increasing or decreasing in value and any changes to the property over time. So we can take this hierarchical relational data set and put it into a denormalized data set. And what you see here is a illustration of grabbing a single record, all the fields from the people record, and then all the vehicles that are associated with that person, and putting it into a cohesive record structure, then followed by property information and the tax data that's associated with that one particular piece of property, and another piece of property at the end until we get to the end of the record. Now this was also done because we actually had a need for getting this information to our customers out in a 9-track tape format. So a lot of times we would take our normalized data sets, denormalize it, and then output it to 9-track tape. So I'm not sure how much we do that anymore, but that's the little picture in the upper right-hand corner, the mad scientist with the tape machines going. But this is an illustration of a denormalized data set. Now, how do we do this in ECL? Well, it's simple. First of all, denormalization can utilize what we call a nested child data set. And the nested child data set is ideal when you have multiple children that are associated with a particular parent, and the number of children can vary. So a lot of times we'll show a denormalized example that's not using a nested child data set because the number of children for each parent is fixed. So a lot of times a solution to denormalization may not show a nested child data set, but in real world stuff, most of the time you'll see a nested child data set representing a parent-child or a denormalized data set. So you see here the parent record is showing addresses, and the child record is the people that live in a particular address. So we actually add to the record structure a data set statement at the bottom that shows a child record, the name of the record that's above, and the name that we give it, we're calling it children, and we're allowing no more than 20 people to live at a particular household. The data set statement below shows the name of the file, references the parent record, and this is a Thor file, which a lot of times people see Thor files as fixed length records, but in this case, because we've added a nested child data set, it becomes variable length. All right? So how do we do that in ECL? Well, how do we take the normalized data sets and then create a denormalized data set? We have a special function in ECL called Denormalize. And Denormalized is actually a specialized join. It's built for taking a parent-child relationship and giving a resultant denormalized output. So the first parameter is the parent output, which is our parent record, already formatted with the new information that is necessary for each child record. So we take that basic parent record, we have to pre-process it. And we can use either a project or a table to do that. So we use a project or a table to take the original parent, to project the output to a new parent record structure that has made room for the children. And the denormalized then second parameter is the actual child record set. The condition of join is what is the linking field between parent and child, and then of course the transform that actually does the transformation. So again, it's like a join. It's using a left and a right record structure and then an optional counter, which is very useful for keeping track of the number of children. And, well, that's about it. So the parent-child relationship, well, yeah, the other point I want to make here is how is this different from the normal join? Well, the parent output will sit, as long as the condition is true, the left record will remain persistent in memory during the process as long as the condition is true, so only one copy of the left record remains, and multiple child records then get added as needed. So unlike a join where you'd have parent-child, 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 you'd have duplicate parent records for each join. This is where Denormalize then excels in working with relational data sets. All right, so once you denormalize a data set, here is the benefit of that denormalized data set. And there's two essential rules that I'm summarizing here on this slide. Number one, the parent record fields are always in memory when operating at the level of the child. So if I'm doing a query on vehicles and it's related to people, as I'm reading each vehicle record, I always will have in memory the parent that relates to that particular vehicle, and I can use that. On the other hand, when you operate at the level of the parent, rule number two, is that we get implicit grouping of the relational data set by child. So once we denormalize, only the vehicles for Bob Foreman becomes in memory, and then Richard Taylor has only his vehicles, and so on. So implicit grouping means that we can take advantage of some more powerful ECL statements like dedupe with all and some of the powerful sort operations that may require grouping from time to time. So by operating on the level of the denormalized data set, we can then take advantage of these more powerful statements. Also then we can take advantage of more powerful querying. Now the last thing I want to show you here before I attempt to go out and show you a couple of ECL examples is the normalize function. Well, this is going the other way. This is taking a denormalized data set normally and then normalizing it. So what's interesting about normalize, which people that are in my class, their ears perk up when they see this, is everyone's always complaining about ECL doesn't have a loop like they want where I can manually loop through a number of records and do something. And then they see normalize, and they see the second parameter of normalize being a numeric expression specifying the total number of times to call the transform for that record. So yes, you can control how many times for each record in the record set, how many times do I want to call the transform. Now what this is designed to do, though, is to take an original denormalized data set and extract the contents. The expression field is normally the number of child rows for each particular record. So the expression would say something like left.vehicle records or left.property records and so on. That would give the counter of that. So it'd be vehicle count or property count, which would then be a numeric expression for telling for each parent record that's being read how many child records, how many times we need to call the transform and then extract the children. There's also a second form of normalize that if you don't have the child counter available, you can simply reference the name of the nested child data set. So then you can say left.vehicle recs, or you can say left.property recs, whatever the name of your nested child data set is, and normalize will automatically then go to work for you and extract all the child records referencing the nested child data set. All right, so now I'm going to very quickly try to share my screen, and I have to apologize to all of you out there. I wanted to do this. We went through a kind of a rehearsal before we went online, and for some reason I couldn't get it to go, so I'm going to cross my fingers here, and we will see if we can do this. So I'm still here. Bear with me. And it looks like we're there. Ta-da! All right, that's good. I know you can see what I'm seeing, so I'm going to Alt-Tab over to the ECL IDE. Let's see. Here we are. Okay, so here is an example of a denormalization process that we go through in class. So what I'm doing here first is showing you, here's our people layout, the original parent layout, and here is our vehicle layout. So step number one is we're creating a new denormalized record structure. Here is the nested child data set. Once again, the child record, which I have exported in another file. I'm calling my nested child data set vehicle recs. And then step number one, we use a simple project to make room for the children. So we're taking the people file. Our output is the layout of the denormalized data set. And by the way, we're wrapping this in a module because I have two exports inside here. I have the export of the record structure, which I'm going to reuse, and the export of the actual denormalization. So step number one, up to line 13 here, is making room for the children. And notice that this parent-only definition is used as the input to our denormalize function. So the denormalization uses the parent record that has room for the children, the actual child record set, our linking field, which is an ID, and then we're passing it a left and a right and a counter. Left and right is required, counter is optional. So the counter here is keeping track of the number of child records, number of vehicle records per parent. Here we're doing a simple append, taking left record that remains persistent as long as the condition is true, and then appending it all additional child records that are necessary. So this will create a parent-child of people and vehicles. So in our class, we go through, we do the same thing for property and tax records. We then take the result of this first ECL code, the second one, and then we have a final denormalization combining the data sets together, combining our counters together, and producing a final denormalization. Now, yes, you could do this all in one file, but in our training, I like to break down the task into small pieces. But you see that the code pattern for denormalization is pretty similar in all aspects. You know, again, number one, make room for the children using a project or a table, and then number two, taking that result of your project and denormalizing it. Once again, the important thing about this is defining your denormalized data set. This is just a simple module that is now drilling down to the child records by referencing their label of their nested child data set. So now we are all in this one denormalized file. We still have the ability to query into the parent or to query into the individual child information or to even query down to the tax data information, which is a grandchild related to people. Here's a quick example of something we would do. Now, and think about this. How would you do this if you had normalized data sets? In this example here, we're looking for properties that are on a small street that have a valid total or assessed value, and if they do have a small property, give me the sum of all their properties, otherwise return a -9 code. And how does this apply? Well, here's a quick example here of just outputting the denormalized data set and then a number of different queries that I've put together here. And when we look at the result, here is the denormalized data set. I'm going to zoom in on this real quickly. And you see that we have some queries that I wrote. First of all, this lady, Petronica Spock, which this is all just training data. These people do not exist. She has property on a small street that is a sum total of $356,000. These two people right here have a -9, no small properties, and so on. Here's another query that shows vehicle new trucks. Who bought a new truck and what was their price of the truck? You can see this data is a little outdated. If I could get a new truck for $16,000, I want to know that dealer's name. Here's the prop tax data home assessment, and then how many unique make vehicles do they have? Are these people collectors of vehicles, or are they loyal and maybe only buy Fords and only buy Toyotas? All right. And the last thing I want to show you is once you get to from the denormalized state, how do you normalize it? This example right here. Let me just zoom in on this real quick. All right, so here we're taking the denormalized data set, normalizing it back to its original format using either Form 1, using the counter, or Form 2, using the actual label of the child data set. But guess what, gang? It even gets simpler than that. I think it was version 3.10 of the HPCC where Gavin had released a new form of project. And I like to talk about this because a lot of people don't realize you can do this, but you can take a project and you can say, here is the input of the project and here is the output of the project, and just match the fields up. So in essence, what this is doing is normalizing my denormalized data set. Starting with people, I'm only giving the matching fields from the original people layout. Here is the reference to the child records, and give me only the child fields and so on. And so you see I'm extracting it into 4 normalized outputs. Back to people, back to vehicle, and here's property, and here's tax data. All right, last thing I want to show you, and I'm going through this quickly because we're, again, our time here, is, yeah, you can even index denormalized data sets, and I wanted to show you an example of this. Here is, let me just type in the last name here, Richard Taylor, and let me submit. And as you can see here, I built an index on people and vehicles. So just real easy here, using Roxy, I can just look a glance at, well, here's a Masaki Taylor with 6 vehicles and the vehicles that they own and so on. And so very easily you can build indexes on these denormalized data sets and actually run queries on them and extend your analysis. All right, so back over here, and let me stop my screen share. And we'll go back over to our slides. And in summary, using a denormalized data set can improve the power of your queries and discover hidden relationships in the data. ECL has a powerful and easy support in moving from normalized to denormalized back and forth when needed. And knowing how to move both ways and best practices in doing so is a good skill to have for all of your for all ECL developers. And finally, the whole motto of this in our Valentine's special is to love your data. That's the important thing. All right, so one last question, if you're still around after today's ECL Tech Tip, will you plan to use Denormalize for any advanced query applications? All right, so let's take a look at our list right here. Let's look at some poll questions. Well, I have one person with 100% on that. Will you use Denormalize for any advanced so far? They probably have 2 votes. There we go. Good. Excellent. Let's see what else we have. There we go. First poll, have you ever worked with a relational denormalized data set in ECL? All right, 28% yes, 71% no. Fantastic. You know, I'm so glad that you guys attended this because it's a nice thing to know about, a nice tool to have. We have advanced, and another reason for this is, of course, I was promoting the advanced class. You have more time to actually work with this in the advanced ECL class. You can learn more about denormalization and normalization in our online training or in the next class that I'm presenting in Alpharetta in April. Maybe some of you in the Alpharetta area, I will see you there. All right, and last, let's go to the questions from the audience. Let's start with, is there an easy way to easily flatten a data set with child data sets? Well, I guess that's what I was doing there with the denormalization. That is the way to do that. So flatten the data set means to have a single record that's encompassing all the child data sets within it. Yeah, and sometimes, like I said, you know, you have a series of denormalization that goes on. You know, you can only do parent-child one at a time, so sometimes, you know, your process might be multiple denormalizations that are going on in the same file. Can you have a, next question, can you have a hierarchical nested child data set in a Russian doll fashion? For example, real estate properties for a person, including the value of each property for a number of years. All right. Yes, I imagine you can. I mean, I'd have to look and visualize the data a little bit more. I understand the Russian doll analogy, real estate properties for a person, including the value of each property for a number of years. Sure. I mean, you can always do pre-processing on a data set too and do things like crosstab reports and do summarization data sets and then denormalize upon that as well. So yeah, the sky's the limit for what you can do with this as long as you understand the data that you're working with and love the data that you're working with. All right, so that is all I have, and I want to thank everybody for attending. And as we conclude, next month, I think March 15th is our next Tech Talk. It's shown in the bottom of the slide. We already have a person, Itama, who is affiliated with Wayne State and Kaiser University, who's going to be talking about conducting exploratory data analysis in educational research using HPCC systems, and he's going to highlight the concepts of merging math identity with self-efficacy. So look forward to that one in March. And if you have a story to share, or you want to pitch a new use case, you want something you want to demo, we're always looking for people to present at these tech talks. And again, I want to thank Raj and James for the February Valentine's Day session. And with that, again, our download tech talks for this, if some of you are like to look at this later on, there is the link below for the wiki, and for the events page, you'll see the recorded information for each tech talk. All right, so the last slide here, there we go, and thank you so much for attending, everyone. Really appreciate it. Trish, you want to say something on the end of it?
Nope, that's a wrap. Thanks everybody for listening, and we look forward to having you join us next month.
All right, thanks everybody.